Hello and welcome to this clip on periodic trends for Group 7. This is intended to replace the original clip on periodic trends and halogen reactions, which ended up lasting about an hour, so I've edited it back down just to cover the physical properties, the trend in reactivity, a little bit on disproportionation, and the use of chlorine in water purification and bleaching. If you're looking for stuff on the redox reactions of halides and halogens, the displacement reactions and the ionic equations, the reactions with silver nitrate, etc. That's covered in a separate video called Halogen Reactions Quick Version. But we will have a look at a worked exam question that will come at the end of the clip. So all halogens take the form of a diatomic molecule, and as such, because the electronegativity of each atom in that molecule is identical because they're the same atoms, you're only going to get London forces, and it's going to be non-polar completely, the molecule. So London forces are going to be the only intermolecular force that have to be overcome during changes of state. So basically, the state at room temperature is completely dependent on the strength of the London forces and nothing else. So if you look at the diagram on the left where it says the boiling point increases as you go down the group, the reason for that is that the size of the atom decreases as you go down the group. What I wanted to say was it increases as you go down the group, so the size of the atom increases as you go down the group. Apologies for that. So this controls the London forces, in other words. So taking examples such as bromine on the right, you can see in the animation that in that photograph, obviously the vapour is coming off the liquid, and what's happening is the London forces are being overcome very easily at room temperature, so the vapour that comes off is quite thick, quite soupy and dense. So the boiling point of bromine is something around 59 degrees approximately. Chlorine and fluorine are smaller molecules, smaller atoms in those molecules, so they're gases already. Iodine, by comparison, has a very large sized atom compared to bromine, so therefore it's a solid. But even still, if you look at the photograph of the iodine in a sealed container down at the bottom left of the screen, you'll see a slight purple tinge. So the grey solid that's coating the inside of the sealed container is the iodine as a solid, but the purple tinge is the iodine vapour that's starting to be given off at room temperature. So even iodine, the London forces, although they're a bit stronger, they still are not strong enough to not be overcome at room temperature. So now let's have a look at some of the chemical properties on a simple scale of the halogens. So the reactivity of the halogens is entirely dependent on their ability to gain an electron. So all of the clips that you saw on the previous screen were involving the halogen atom gaining an electron from another species, another atom, another element of some kind. So if you look at the relative sizes on this diagram, it's not necessarily to scale, but the relative sizes of the atoms, you can see that fluorine is a very small atom and the astatine is a very large atom. So as you go from left to right, effectively descending the group, the reducing ability increases. So when I say reducing ability, I mean the ability for the atom to reduce something else, to cause something else to gain an electron. So therefore it's easier for the atoms to lose an electron as they get bigger. Obviously this is down to shielding and lowering of the nuclear attraction. In spite of the fact that there's more protons in the nucleus as you descend the group, you also get extra electron shells, so therefore the extra shielding offsets the larger proton number. So if you take anything from this screen, just have a note down the fact that as you descend the group, the reducing ability increases, but as you descend the group, the oxidizing ability decreases, and the reason for both of these trends is in purple at the bottom. Okay, so let's look at some examples of redox reactions of the halogens. So here's a selection of clips that just show how reactive the halogens are. Fluorine in particular pretty much reacts with everything else because it's able to remove an electron from virtually every other element on the periodic table, so it's the most powerful oxidizing agent, at least the most powerful elemental oxidizing agent that we know of. A couple of interesting ones with aluminium, reacting with iodine and bromine. And you may notice that they create the compounds with Al2I6 and Al2Br6. This is evidence of something called dimerization, but that's slightly beyond our specification, so I'm not going to go into it in this particular clip. Apart from saying that all that happens is it's basically two lots of Ali3 that actually bond with each other chemically to make Al2I6. If you wanted to look up online dimerization of aluminium halides, there's plenty of images and websites that can go into this further. But like I've just said, it's outside our spec, so I wanted to avoid confusion here by not going into it too much. Right, so before we go any further with the specifics of this reaction, it's worth introducing you to a term called disproportionation, where you get simultaneous reduction and oxidation of the same element in a redox reaction. Although at first it might sound a bit strange, what you're not doing is simultaneously reducing and oxidizing the same atom of that element. So it obviously means you've got to have two atoms of that element. And as we've mentioned before, halogens are diatomic. So let's have a look at this in action. So the first thing to do is to obviously give everything an oxidation number. So let's do that first, and then we can decide what's happening. So we can see that hydrogen and oxygen don't change their oxidation numbers. So neither of them are involved in oxidation or reduction. So let's have a look at chlorine a bit more closely. If we follow this one round to here, you can see it's gained an oxidation number by 1, so it's been oxidized. But at the same time, if you start from the same chlorine and you go over to here, the oxidation number is decreased by 1, so it's also been reduced. So we can see quite clearly that chlorine has been oxidized and reduced at the same time, or to be more specific, one of the chlorine atoms in Cl2 has been oxidized whilst the other one has been reduced. So this phenomenon is called disproportionation, and it's one to look out for definitely when you're doing questions on chlorine and water or chlorine and NaOH. So this species, HClO, this one here, it's quite interesting because this is the active ingredient in bleach, and it contains something called a chlorate ion, which is toxic to bacteria. And so it's quite often found in toilet bleach of all sorts of brands. So HClO, or hypochlorous acid, contains the chlorate 1 ion. And it's the chlorate 1 ion because the chlorine in the chlorate 1 ion is in the oxidation state +1, as you can see. So the chlorate 1 ion would be drawn like this. ClO minus. And because everybody loves a silly cat video, I thought I'd put one in. Completely random. Make no apologies. I felt like it, so I did. Okay, so now let's have a look if you can actually pull your eyes away from the cat meowing as approval. Now let's have a look at dilute NaOH and how that reacts. That's also a disproportionation reaction, but I'm going to put that down in a second and see if you can actually work out in what way it's a disproportionation reaction. So there's the reaction. Pause the video for a second and see if you can work out what the oxidation numbers are, and then we can take it from there. So pause it now and then come back in a couple of minutes when you've worked it out. So hopefully we're in agreement here. If you're not sure, go back and check your oxidation number rules. So oxygen always taking -2, hydrogen taking +1, sodium being a group 1 element taking +1. So now let's follow what chlorine does. You can probably see it's fairly similar to what's happening at the top of the page. So you start off going from here to there, it's an increase in oxidation number, so it's been oxidized. There we go. And we put increase oxidation number. At the same time, we've got it going to here, and that's a decreased oxidation number, so it's reduced. So this is an example of disproportionation again. So we can say that chlorine has disproportionated. Okay, so now let's have a look at some of the pluses and minuses of using chlorine in drinking water. They put chlorine in very small amounts of drinking water to try and to kill off the bacteria that might cause serious infections. So one thing to consider, and I'm not telling you what to think here, and your textbook won't tell you what to think either, it's just something that you need to be aware of. The risk is that chlorine can react with organic compounds that we find naturally in drinking water to produce carcinogenic chlorinated organic compounds. At the same time, millions of lives have been saved since we've started chlorinating drinking water from bacterial and protozoal diseases such as dysentery, typhoid fever, cholera, and more recently things like cryptosporidium protozoan. That's quite a modern problem. And it's affected us here in the UK quite a lot. There's quite a few water companies who've fallen foul of cryptosporidium. Now, all of these listed germs you can see in the table can actually cause death. We're not talking about just a simple tummy bug, we're talking about things that can actually kill you. So it's very, very important we do something to stop millions of people drinking inadvertently these types of pathogens. At the same time, the poster at the bottom focuses on the toxic dangers of chlorine. Chlorine itself is toxic, but the main problem is the insidious nature of some of its compounds, the carcinogens, haloalkanes and things like that can creep up on people over time and cause premature aging as well as cancers and birth defects. So the debate rages on. So in terms of what you need to know, you just need to be aware that there is this risk versus benefit consideration, and you don't have to necessarily have an opinion on it, although you may well do. I do, but I'm not going to put it on this video because it would be wrong. I'm just going to leave it for you to decide where you stand. Okay, so we're coming towards the end of the clip. We've covered pretty much all the stuff that we need to do, apart from the testing for halide ions. That's another one that we really need to cover, and this is using silver nitrate. Okay, so what I've done is I've taken a selection of exam questions and sort of hybridized them into one to try and pull in as much of the material that we've covered in this clip as possible. So let's start with something fairly straightforward. There's a paragraph just explaining a little bit about something called the chlor-alkali industry, and explains why it's called the chlor-alkali industry. And it makes reference to, in the first part of the question, bleach can be made by reacting chlorine with cold aqueous sodium hydroxide. And then a solution of bleach contains the chlorate compound NaClO. So in actual fact what they're doing is giving you what you need to write. So let's have a see what I mean by that. you're reacting chlorine with cold aqueous sodium hydroxide. It's actually given you what two things are reacting. So we now know that we can put NaOH plus Cl2. You might notice I'm not putting state symbols in here because the question hasn't asked me to do that. Okay, so this is a solution of bleach contains the chlorate compound NaClO. So it also tells us that that compound is there as well. So we can write that in. And the rest will be from memory, from having revised this. So let's think about what else you might get. Well, we know that it's likely to be something to do with disproportionation, because if you've done your revision on sodium hydroxide reacting with chlorine or water reacting with chlorine, you'll know that both of them are disproportionation reactions. So we've used up one of the sodiums in NaClO. It's highly likely there'll be another sodium compound, such as NaCl perhaps. So I'm going in the dark a little bit here, but I'm also playing devil's advocate. I'm pretending that I don't know what I'm doing, but at the same time I'm pretending I don't know what I'm doing because I'm a student that may have not revised this, and I'm trying to work it out from first principles. So I know that might seem strange to put in a second sodium containing compound when there's only one sodium on the left. But you'll notice it's got a hydrogen in it, and the hydrogen wasn't included in the NaClO, so you're going to have to use the hydrogen somewhere as well. If you double that up, that now means you've got the two chlorines taken care of, and also the two sodiums taken care of. So the only remaining thing to do really is the H2O. And that gets us our mark. So the systematic name for NaClO is sodium chlorate 1. Now, it's highly likely that NaClO3 is also going to be called a sodium chlorate, so we can definitely write that in, can't we? Now, all we have to do is work out what number goes in there. So leave a space for it, and we can now think it through. If we think it through systematically, we'll know that sodium is going to be +1 like it always is, and therefore the chlorate ion, this particular chlorate ion, ClO3, is also going to be -1. So if it's -1, that means that you have to think about what the chlorine oxidation state might be, because that's where the 1 comes from in sodium chlorate 1. So what I mean by that is that's 3 lots of -2, because oxygen is always -2. So if you have 3 lots of -2 and you need to make it up to -1, that must mean that the chlorine is +5. So therefore, we put in a Roman numeral V for 5. So the next part of the question says, when heated, NaClO3 disproportionates as shown in the equation below. And I've forgotten to put the equation in, so I'm just going to pause and add that in. So you can either do this in words, or you can do it by the diagrammatic method, which is simply just annotating the equation with the oxidation numbers and then drawing in whether each change is oxidation or reduction. So we don't have to worry about oxidation numbers for sodium because it's always going to be +1. We don't have to worry about the oxidation numbers for oxygen because it's always going to be -2. So let's have a look at the chlorine. So first of all, we know that it's plus 5 in NaClO3 because we worked that out in the previous section of the question. The next part is a little harder, but using the same principle that we used in NaClO3, if it's NaClO4, 4 oxygens means 4 lots of -2, which means -8, and you can see that the proportion of sodium to chlorate this time is still 1:1, so therefore sodium will still be plus 1, and oxygen will be 4 lots of -2. So therefore, for the whole thing to be neutral or 0 overall, the chlorine has to be plus 7. So now what we've got to do is work out what does that mean in terms of reduction or oxidation. Now if you remember what disproportionation is, it's a simultaneous reduction and oxidation of the same element. Now if you look at the NaClO3, you'll realise that there are 4 of them. Okay? So therefore, we can now say that we have 4 chlorine atoms to play with. So if the chlorine goes from here to here, it's an increase in oxidation number of 2, so that means it's been oxidized. And if we now look at the same chlorine, and we move over to here, it's dropped quite a bit in oxidation number, so that must mean it's been reduced. So to sum this up in words, you need to think your way through it carefully and then just put it together. So you've said that chlorine has been reduced and oxidized. You've said what oxidation state it was in, what it's gone to when it's been reduced, and you've said what oxidation state it was in and what it's gone to when it was oxidized. You said that sodium chlorate, and it was 5, or V in Roman numerals, that gets a mark there as well. So, because this clip was mainly about the trends in the group, and a little bit on the reactions of chlorine with water and chlorine with sodium hydroxide, I'm not going to cover the remainder of this particular exam question because that is more about the displacement and testing for halides, which is covered, like I said at the beginning of the clip, on a separate video. So thanks for listening, appreciate your time, and if you want to follow on and have a look at the other video clip, it's called Halogens Reactions Quick Version on Jason's Chem Clips.